Hi there, Earth Systems sustainability people. This week we're going to be looking at water chemistry. And I'm going to be asking you to take some bottled water samples and understand the chemistry of that water by looking at the label and working out where that water's come from. So this is the 1 week I'm going to ask you not to be very sustainable and to go and source some water, and we'll learn about water chemistry in the class. I'll see you there.
This week's topic is water chemistry, and it's assessed by the assignment where you'll be looking at some bottled water quality information from drinking water bottles. I've divided the topic into these 4 themes that you can see listed on the left-hand side. My background is a water analyst. I've worked in both riverine, groundwater, surface water, and engineered water systems that includes drinking water and wastewater. And there's some pictures on this slide showing some of the research and undergraduate students at different sites around New South Wales. If you would like to follow up this presentation with some further reading, maybe to get more clarity on some of the topics, I strongly recommend the presentation by Bruce Welsbach on his Earth Scientist Periodic Table. It gets quite technical, but the first part of that presentation is very good, and I use that table in subsequent slides, as you will see. And I've also provided some references here related to bottled water quality, its lack of sustainability, and why people might rely on bottled water. And they relate more to the assignment that's related to the topic this week. And here is a link again to the Earth Scientist Periodic Table. I will show some zoomed in versions of this in a subsequent slide. I just repeat it here, and also note that if you go to the website, you'll find this available in multiple languages. So if English isn't your first language, the chance is that it has been translated into a language that you might find preferable. The first theme as part of this topic is the theme of inorganic solutes. And the key points to know here is that the water molecule, so the water that makes up our rivers, lakes, groundwater, marine systems, is polar. And the polar nature of water makes it a good solvent for molecules that are also ionic and polar. So this is shown in the top right hand side. This is a water molecule here, which is made of H2O, so 2 hydrogens, there's one, there's the other, and 1 oxygen. And the way that the oxygen and the hydrogen bind in a molecule is that it's not completely balanced in terms of the charge, and there's a little bit of a negative charge on the oxygen part of the water molecule and a little bit of positive charge on the hydrogen parts of the water molecule. And opposite charges attract, so that means that if you have another element in the water which has a slight negative charge to it, then that will be attracted to the slight positive charge of the hydrogen in the water. And if you have an element which is slightly negatively charged, it would be attracted to the positive part of the water molecule. And the example for that that's given below is salt dissolved in water. So salt is sodium chloride. There's the sodium Na+, and here is the chloride Cl-. And as salt, the sodium and the chloride, the Na and the Cl, are combined as one molecule, sodium chloride, and the charges, the one positive charge on the sodium and the one negative charge on the chloride, they balance, forming salt. It dissolves in water, and you can see here that the sodium with the positive charge becomes soluble in water because that positive charge can be aligned or attracted to the negative part of the water molecule. As you can see here, the oxygen's all aligned. This time they're in red, and the chlorine, which has a negative charge, is attracted to the positive parts of the water molecule, which is the hydrogens, which in this version are in white. So that's broadly summarized in this middle paragraph here. Natural waters are water-based solutions or aqueous solutions with other elements and compounds, which are called solutes, dissolved in the water. And most solutes in natural river and groundwater systems carry a charge, either as a cation, which is positively charged, that's the sodium example, here, the positive charge, or as an anion, which is the chloride with the negative charge here. And some molecules are non-polar, so they don't polarize, they aren't charged, and they have little affinity for water molecules. And these will largely be organic molecules, and we'll discuss those in a later slide. So let's look at that another way and use the Earth Scientist periodic table. And I've zoomed in to just one small part of this periodic table. One of the good things about the way that Bruce Welsbach has designed this table is it actually provides you information that you might need to know as an Earth scientist. So this looks really complicated because it combines out so many different bits of information at once. But if we just look at the colouring, which is blue to start with, the blue symbols show the different elements that you're most likely to find as a dissolved solute in different environmental systems. So you have some blue symbols with an M in them. So here's one over here, which says that that element, in this case it's magnesium or Mg, is most likely to be found in marine systems. So it's dissolved in ocean water. And so you'll see magnesium has that symbol, but also here's the symbol again for calcium, and also here for sulfur, and at a slightly lower level here for phosphorus. We also have symbols for rivers, for freshwater systems. So again, we have sulfur, we've dissolved in river waters, a small amount of silicate or silica as silicate. We also find calcium and magnesium. We can also use this table to identify elements that are more likely to be found in sediments in the geological record, and by implication these would be elements that are less likely to be solubilized. So the ones with the S symbols here, we have aluminium, titanium, silicon also, so it's more likely to be insoluble than it is to be soluble, zircon, and so on. So one reason for having the Earth Scientist periodic table at hand is that if you get confused or uncertain about how an element might behave in the natural environment, you can look it up in this table and you can find all sorts of information out about it, and that's why I recommend it. The second theme that I wanted to introduce in this topic of water chemistry is the world of organic solutes. So we have inorganic solutes, which are the elements that you can see in the periodic table in the previous slides, and organic solutes, which are predominantly based on a framework of carbon atoms. And rather than being bonded ionically, they are bonded covalently to each other and to other elements. And there's a huge range of organic molecules. And if you read any of the papers or literature, you'll see some terms that appear many times. And one useful term is that you will come across straight chain or branched chain molecules, and these are called aliphatics. And you also have carbons that form ring molecules, and these are called aromatics. And these define their solubility in water. So the example on the top is a straight chain or an aliphatic organic molecule, where we have, in this case, 2 carbons in a row. At the end, there's another oxygen and hydrogen bond. This is an alcoholic bond, an OH bond, and similar to water, when you have an OH part of a molecule, it becomes polar, and we have a slight negative charge again on the oxygen and a slight positive charge on the hydrogen. So this compound is an alcohol because it's got an OH bond on the end, and because it's got the OH bond on the end, it's polar, and because it's polar, it means it's soluble. And that's why if you drink an alcoholic beverage, you can actually mix it to form cocktails, because alcohol does have some solubility in water. The lower example is a carbon ring structure. So this has 2 carbon rings. This is one of a type of carbon molecule called a polycyclic aromatic hydrocarbon, often abbreviated to PAH. And this example is of something called naphthalene. And naphthalene was made as an ingredient in mothballs. has a very distinctive smell, and it used to be put in people's clothes and in cupboards to keep moths from settling there. And naphthalene is a carcinogen, so it's not so commonly used now. And it's found as an environmental pollutant, actually, as a leachate from leaking landfills. So that's two examples of the different types of organic molecules that you might have. Naphthalene doesn't have this polar component to it, so it is only very poorly soluble in water. In general, organic matter in rivers and groundwaters are derived from biological material, from the breakdown of soil material, from plant material, humus. And humic substances is a term that's often used to describe this soil-derived organic material, and you'll see that used in the literature. And often organic matter solutes are measured in water samples, and they're filtered at different filter sizes. And the truly dissolved organic carbon fraction is a fraction that's been filtered at 0.45 micrometers. And anything that stays on the filter paper when you filter at 0.4 micrometers is then defined as particulate organic carbon. And organic matter can be both dissolved and particulate. And in fact, it can actually be somewhere in between, something called a colloid, which we featured in the next slide. The reason for including a slide on organic solutes is that they are the food for river and groundwater ecosystems. This provides the carbon that's necessary for the microbial food web, which then builds up to higher life forms, invertebrates, fish, and so on. As I said, the actual reality of how elements and molecules interact is a bit more complicated, and in most aquatic systems we should be looking at colloids rather than just the dissolved or just the particulate fraction. So this slide shows an example for coastal waters, and it shows the different size ranges of colloids, dissolved and particulate material. So here's the dissolved range here, going up to this 0.45 micron scale, and bigger than that we have particulates. And the colloid range is defined as being between 1 micron and 1 nanometer. So this cutoff here at 0.45 is a bit arbitrary, and it actually cuts off in the middle of a colloidal size range, which is not very sensible. You'll see on the lower side of this figure with all the colors, you'll see a whole range of different bacteria, viruses, zooplankton, so other features to give you some sort of idea of the size range. And you'll notice that the scale here, which is in meters, is on a logarithmic scale, so there's an order of magnitude change between each one of these tick marks. So the colloidal size range that we're interested in is the same size range as some of the bacteria, all of the viruses, and all of the nanoparticles as well. And it's in this range that the organic and the inorganic elements and molecules interact, forming these colloids, and they get transported in aquatic systems. Next, I would like to consider chemical reactions. So let's take a water sample. Let's say you've got a water bottle, or you're drinking some tap water. There will almost always be far fewer solute molecules than water molecules in that water sample that you have, and the bottled water exercise will also demonstrate this. If you look at the chemistry on a bottled water label, you'll probably find that the concentration of the different solutes, let's take for example calcium that's dissolved in that water sample, will be measured in the parts per million range, ppm. So for every million water molecules that you have in your bottle, there may only be 10 molecules of calcium. So that makes it quite hard for chemical reactions to occur, because the actual elements have to interact in this huge sea of water molecules. It's only when they actually interact that you might get a chemical reaction taking place. If you have a closed system, so again, let's visualize you have a drinking water bottle with the lid on and you don't do anything with it, it's full. There's no inputs, so you're not adding more water to it. There's no outputs, you're not drinking it. The amount of air in the top stays the same. Then the chemical reactions will proceed to an equilibrium where all the reactions could have taken place, have taken place, and all the concentrations stabilize. And the rate of a chemical reaction will depend on how frequently there are collisions between these reactant molecules. So if the bottle's warmer, they might have greater diffusion rates, they might interact more frequently. And also the number of those collisions which are energetic enough to actually cause a reaction to occur. I'll give an example of this in the next slide. And the example I'm going to use quite frequently throughout these slides is the example from the carbonate system, which is shown on the right-hand side. So this is a nice picture of stalagmites growing in a cave, and the stalagmites are made of calcium carbonate, which is CaCO3, which is this part of this equation here. And calcium carbonate is also limestone. And limestone, when it dissolves, it reacts with water and carbon dioxide. These two form a weak acid, carbonic acid, and that then dissolves the limestone and it forms calcium in solution and the hydrocarbonate ion in solution. And you can see in the middle here there's this two-way arrow which suggests that the reaction can go in both directions. So above the cave, this reaction is taking place in the soil and the geology. You will have the reaction going from the left, from having limestone bedrock, that will be dissolved and it will go to the right, and in the water system above the cave you will have dissolved calcium and dissolved hydrocarbonate. And then when you get into the cave, this reaction goes the other way, and this dissolved calcium and hydrocarbonate releases carbon dioxide and water and forms calcium carbonate again, this time in the form of stalagmites and stalactites. So I'll use that example in the next few slides. First of all, talking about the rate of chemical reactions. Let's use the growth of stalagmites then as an example for understanding the rate of chemical reactions. What different factors affect how fast stalagmites grow? This is quite a busy slide, so I'll talk you through it quite quickly. On the vertical axis, then we have the deposition rate in millimeters per year. This is how fast a stalagmite grows. So you'll see from this that a stalagmite will typically grow maybe between 1/10 of a millimeter a year and maybe 1 millimeter a year. What makes it grow faster? So what makes a faster deposition rate? So figures that are up here. Well, you can see, first of all, if you have more calcium in the water, some more dissolved calcium ions, then you get more growth. That makes sense from the equation on the previous slide. If you've got more of the reactant on the right-hand side of the equation, and the equation is going to the left, then you produce more of the product, which is going to be the stalagmite. But you also see here there's different temperatures. So this is an experimental study, and you can see that at 4 degrees centigrade, you get much less stalagmite deposited than at 10 degrees centigrade than you do at 20 degrees centigrade. So as you warm up the solution, you get greater chance of the reactants to interact. They're more energetic. They have more chance to exceed the energy needed to actually form calcium carbonate. So the warmer the solution, the faster the growth. And also you can see within that scale, these figures here, this is how much water is above the stalagmite in the thickness of the water. So from 0.05 millimeters to 0.1 millimeters to 0.2 millimeters. So the greater the water thickness on the surface, then the faster the growth. And that then tells us that the more water on the surface, the greater provision is going to be of calcium and hydrocarbonate, and that's also going to speed up the growth. So you can see here, just for one example, there's an order of magnitude rate of the chemical reaction depending on things like the supply of one of the reactants and the temperature that is occurring. We can also consider the equilibrium of a reaction and whether reactions reach equilibrium quickly, or maybe some will never reach equilibrium and they're continuously reacting very, very slowly. And in chemistry, there's a rate constant for a reaction K, and that can be defined for every single chemical reaction. But in terms of systems, we're probably going to be more interested in some of the reactions that we're going to encounter at the Earth's surface or in the Earth's atmosphere. And I've listed here then some of the typical times that it takes for a reaction to complete based on the reaction type. So starting here with a solute reaction. So this is a reaction taking place between two different chemicals that are dissolved. So it could be two solutes in a river sample or groundwater sample. That would typically be quite fast. So it could be very instantaneous to a matter of minutes. Some reactions involve sorption and desorption of the chemicals from a surface. Let's go back to the example of a colloid. You might have a colloid particle in a river system, and it comprises of both organic and inorganic elements, and the colloid has some internal energy there, which means it's quite securely bound to each other, and it's much harder then to dissolve some of the material from the colloid to then take part in the chemical reaction. So depending on the nature of the colloid and the nature of the solution around it, that could be instantaneous, or it could take days to dissolve. We could have reactions between a gas and a solute, so we actually have to get the gas interacting with the liquid phase. So when there's a phase change, often the reaction is slower. And typically here the timescale may be minutes to days. And mineral solute reactions, so this could be between the bedrock and a groundwater that's flowing through the bedrock. That reaction could take hours, but it could also take millions of years. Some minerals are highly insoluble. If you like a broad generalization which is relevant to what you may encounter in a system, then I would suggest that a regional groundwater geochemistry, so that's a groundwater that has been under the surface for a considerable amount of time, is more likely to be in equilibrium. It's had a chance for all these different chemical reactions to proceed closer to equilibrium. But a river sample, I would suggest that geochemistry is never likely to be in equilibrium because it's an open system. There's new reactants being supplied all the time from the atmosphere, and it's a fast-moving system. So the slow mineral reactions won't have reached the end of their reaction. And understanding this is important, not just for understanding the Earth system, but also if you're interested in sampling water and preserving water samples for further analysis. It helps to understand that the sample you collect in the field is probably still reacting, and it's going to go and want to react in the water bottle that you've collected it in. And that leads you to strategies for what you might want to do to that sample to stop it reacting as soon as you've sampled it. I'm going to use the same example again from limestone, calcium carbonate, to highlight the speed of the dissolution reactions and whether a reaction can reach equilibrium. The picture here is of a limestone surface, so it's bare rock on the land surface, and you can see some fractures there, and the fractions have been widened, so the limestone's been dissolved. And you can see all these solution features here. So the chemical reaction on the bottom of this slide has progressed from left to right. Now the question is, how quickly does it take limestone to dissolve in water and carbon dioxide reaction? And the data in this paper gives you some answers. It's a very poor quality figure. Unfortunately, that's the quality of the original scan in the paper from about 30 years ago now. And it's some original research that was done to actually look at the dissolution of calcite in this case. So there's a calcite sample, and there's some natural limestone samples. And calcite is also a form of calcium carbonate. So we have time since the start of reaction going from left to right on the horizontal axis, and you can see this goes from 0 to 120 hours. And you can't read the caption here, but this is the calcium concentration in the solution. This near vertical line here, this is the calcite standard. This is very pure calcium carbonate, no impurities, has a very small particle size of about 10 microns. And the smaller the particle size, it means there's more surface area, which means it's going to be more reactive because there's more surface to react with. And you can see that this probably reaches close to equilibrium in maybe 20 hours or less than a day. You will see that the calcite is completely reacted with the chemical solution. But the natural samples of limestone, they're still reacting. They maybe have reached maybe 3/4 of the way to equilibrium after a day, and they still haven't reached equilibrium after 5 days. So you can see there is this variation in the time that it takes for equilibrium to be reached. And in this natural example, this is a rock solute interaction. For some rock which is actually quite reactive, limestone is one of the more reactive rock types, you can still see that the time scale to reach equilibrium is not instantaneous, it's days. I'd like to quickly look at pH as well. The pH scale is a logarithmic scale, and it's inversely related to the concentration of hydrogen ions in solution. So hydrogen ion is H+. Hydrogen would normally consist of one proton, positively charged, and one electron, negatively charged. The hydrogen ion has lost its electron in a chemical reaction. It's left with a positive charge, which means it's highly reactive. It wants to react with another electron. On the right-hand side, we can see that the scale here then is the acidic end of the scale is a low number, so between maybe 0 and 5 or 6, and the alkaline or base end of the scale goes up to 14, and you get increasing concentrations of protons or hydrogen ions as you go to a more acidic solution. In the natural environment, most of the rivers and groundwater systems that you'll sample water from, marine systems, lakes, will all be close to neutral, within 1 or so pH units of the neutral pH 7. And that's because most of these systems will have started to head towards equilibrium, or maybe even get close to equilibrium. And so the reactions will have completed or come near to completion, and there's less likely to be excess acids or alkalines in solution. The example that I've presented in previous slides is also a good example for the role of pH and acid solutions. So the chemical reaction between calcium carbonate, water, and carbon dioxide, that is a reaction between a base, calcium carbonate, and an acid, which is the carbonic acid formed by the carbon dioxide and the water combined, that part of the equation. And so this is an acidic reaction with a base, the calcium carbonate, and it's the most widely observed reaction in the system, and it explains high concentrations of calcium and hydrocarbonate in many surface and groundwaters, and you'll probably see this in the bottled water exercise as well. A final reason to be aware of the importance of pH is that many metal compounds become soluble in acidic waters and are otherwise insoluble at neutral or alkaline waters. And this is important when you have pollution issues such as acid mine drainage, which is something that's very topical. At locations where you have legacy mines, old coal mines or mineral mines, for example, where they've stopped working and no one is there to actually maintain them, the groundwater levels start to rise and the water starts to react with an acid reaction. It forms acids from the minerals that are present there, and then it mobilizes toxic metals into the surface water systems and causes an environmental pollution problem. And there's an example on the next slide, which is this example from the Australian Geographic that came out in 2022, and the link is at the bottom, and I'd recommend it to you. It's a historical article about Australia's abandoned mines and how they may be rehabilitated, and there's several examples there of sites where there are considerable concerns from acid mine drainage. It's quite an easy read, I recommend that. And finally, I need to introduce the terms of reduction and oxidation, because many of the chemical reactions that take place on the Earth's surface are those that are often called redox reactions. They involve some reduction or oxidation. And these are common on Earth systems because the Earth's surface is a redox boundary. There's oxygen in the air that we breathe, but often a lack of oxygen in the subsurface, in the groundwater, in the soils, in lake sediments. And the definition, or one definition of a reduction and oxidation reaction, this is one you might learn in chemistry, is that the loss of electrons in a chemical reaction is oxidation, and the gain of electrons in a chemical reaction is reduction. And a way of remembering that is that loss of electrons is oxidation, is LEO. In the environment, we also often observe a specific type of redox reaction, which is also an atom transfer. So as part of an oxidation reaction taking place, we also see a transfer of atoms. The example on the slide is from the nitrogen cycle, and you can see on the lower half of this slide are the nitrogen compounds that you'll find in an anoxic, no oxygen environment. So these will be the reduced compounds, and then you see the nitrogen compounds that are more likely in the oxic environment where there is oxygen. So these will be the oxidized or oxic compounds. And we also see an atom transfer as this process takes place. So for example, if we start here at the redox boundary, you'll see the atom transfer as you go from the ammonium up to the nitrite and then the nitrate. And you see the hydrogen is lost, so that's converted to oxygen, and then we go from 2 oxygens to 3 oxygens, and then as we go back into the subsurface, we go back down to 2 oxygens, so we're losing an atom, and then we lose another atom, and then we lose another atom again, so we just got the nitrogen molecule, and then finally back to where we started. This is the nitrogen cycle. So we're losing electrons with oxidation, but we're also having atom transfer taking place at the same time. Atom transfers like that might occur as a metal is oxidized, as it's exposed to oxygen at the Earth's surface. So I put this slide in because redox reactions are fundamental to biogeochemical cycling. And this is fundamental for many processes on the Earth's surface. So that includes the nitrification example that I've given, nitrification and denitrification. It might be important to whether we get methane production, for example, into the atmosphere compared to carbon dioxide and how that links into climate change. And as a rule of thumb, the final 2 points for this set of slides on water chemistry is that the solutes in rivers are more likely to be oxidized because rivers are going to be able to exchange oxygen with the atmosphere. They're free flowing on the Earth's surface. Groundwaters, on the other hand, can be anoxic, but they still can be oxic as well. The way that groundwaters can lose their oxygen is most likely to be through microbial reactions in the subsurface. The microbes need the oxygen to breathe. And so if there is a large subsurface ecology, then you may find that the groundwaters will run out of oxygen because it's been used up by the ecology that's there. But if there isn't a groundwater ecosystem that uses up all the oxygen, then maybe the limited chemical reactions that can take place in the groundwater system can maintain the oxic status. So that's less clear. So that's my introduction to water chemistry. Hopefully that gives you some understanding and overview of the main considerations from a systems perspective, and that you can use that in the bottled water chemistry exercise that follows.